Well, thanks. Yeah, I guess this is the rectangle session with all three there. And it's actually kind of good that I'm right for lunch because it's a relatively light talk in terms of details. But actually, I mean, there are technical details, but what I mean is the most interesting part of the talk, I think, is the problem context and just sort of the, or my discovery that there's this rich geometric set of problems that come from satellite surveillance. So I'll talk a fair amount about the context. Eventually we'll drill down to one specific problem, which is, you know, you have a camera image and some sets of pixels are more interesting than others, and how can you pack some rectangles to cover those more interesting regions. So this grew out of a internal research program at Sandia that, you know, I'm off in the Center for Computing Research, sort of think of it as a CS department. And, but there's many parts of the lab that are much more applied, and there's a big group that helps with the scheduling and monitoring and you know, they don't actually schedule the satellites, but they write the capabilities of software so that other people can. And so we got this internal project to sort of connect this applied to this more theoretical area. And then in the same way, we thought it'd be nice to come give a talk here at CCCG and tell you about this general problem area. And unfortunately, I mean, the original plan was to have Chris Felica come give the talk, and he could tell you all the details about the problem setting, but he couldn't come. I guess that's the downside of being in a more applied group. It's harder to get travel funds and stuff, but I can put you in touch with them. So as I mentioned, the context is there's a bunch of satellites here. There's 4 of them sitting around the Earth somewhere, and you want to monitor certain locations in space and time. The hardware tends to, or the system, hardware and software, tends to be quite specialized with nuanced capabilities that usually aren't captured in the scheduling models. And like many other industrial problems, like airline scheduling or something, getting a little bit more efficiency is a big deal because these things are very expensive and there's very, very few of them. Geometrically, there's some interesting things here going on. So the different sensors, different cameras have different shaped apertures, and also they move, so the projection of the aperture onto the curved surface of the Earth is different over time. And if you're just dealing with one device, you can often just do everything in the image space and not have to deal with this weird projection. But if you have multiple of them and they're time evolving, that can be harder to do. Uncertainty is a big deal. There's things like weather and people change their mind. So sort of a theme I'll come back to is it's handy to have a bunch of alternative plans that you can choose from if something changes. Okay, so all right, so we're going to drill down one level. So first we had all these satellites. Now monitoring a whole bunch of different regions of interest. Now I'm just talk about one region of interest. Can you what's the fewest number of pictures you can take to cover it? And our solution to it was to convert it into this giant discrete optimization problem where you have a bunch of sample points and you have to cover all the sample points, and you sort of shrink the camera image a little bit so that you know if all the discrete points are covered, all the gaps in between are covered as well. And you model this all as some big mixed integer program, and the advantage of that is it allows you to plug it in directly to the larger scheduling problem, which is also a MIP. Okay, so so you can do those kind of weird shapes that I was talking about before. I should have had one that had multiple shapes for a single image, but anyway, so that is not cutting edge geometry there. Sariel basically described this approach in some newsgroup post about the same time we were looking at it. But the thing to consider, though, is that the covering solutions that actually are very geometric tend to exploit like the shape of the image, the footprint is, okay, well, suppose it's a circle. Now let's exploit all these circle properties to show how you can cover this region efficiently, or a square, right? And Karen Daniels had some nice software she shared with us where she did something a little different. Like she said, okay, well, first you have to cover all the corners, and so let's start there, and then sort of eat your way in. So that was an interesting approach as well. But I think overall, this is sort of doing this for very general shapes is sort of understudied. The other weird thing from a geometric standpoint is the complexity is all sort of different. Usually we're talking about the number of sides of a polygon and things like that. And these are usually very small in this context and not really the limiting factor. The problem is usually this giant mixed integer program running time. And so on the plus side, anything you can do geometrically is going to run way faster than this. So n squared algorithm, no problem, because you got a very small n. All right, so next level down, here's our actual subject of the paper. So suppose you've got a satellite with takes square pictures, and you're interested in floods along the Mississippi River basin. So the river itself, that you really care about that. These regions that probably aren't going to flood, you don't really care about. And the way the hardware on these things is typically done is the pixels are grouped into chips. I imagine there's an actual hardware chip in there that captures a set of pixels, but I don't know for sure. And so you get to devote extra bandwidth to some of these chips, and so that's great. So you don't have to. The satellite can take way more pictures than it can transmit them. So the real choice is not what you take a picture of, but what subset of it do you transmit back down to Earth. So it's like we've just modeled the value of a chip to be the sum of the values of the pixels. And then the problem is, can you maximize the sum of the values of the chips that you send down? Because you actually don't get to choose individual chips to devote more bandwidth to. They have this idea of a subfootprint, which is some rectangular subset of the chips, and you get to devote extra bandwidth to each of these subfootprints. And it's kind of weird, the bandwidth that's devoted to each subfootprint is the same. So, for example, like this one that only has 3 chips in it, each of these chips is going to get more bandwidth than the 4 that happen to lie in there. We didn't explore that aspect of the problem, but it sort of points the way to some more variations of the problem that would be worth somebody taking a look at. The other thing is, remember we had a big collection of these photos, and you can move them around a few pixels one way or the other, and you might do that in order to concentrate more of the pixels into single chips, right? They might be easier to cover, or maybe that's not what you want to do because the geometric layout makes it difficult to cover by rectangles if you do it that way. So don't know for sure, but we can explore all these different shifts. And the chips are, I don't know, maybe 50 by 50 pixels, or I don't know, something like that. So you're probably not going to be able to solve 50 squared mixed integer programs in reasonable amount of time to explore all of these solutions. So we're going to do a heuristic to or a greedy heuristic to sort of inform which of those shifts are worth looking at and which aren't. The other thing is, I should emphasize these rectangles, because of the way the bandwidth works, they're sort of constrained by area. If they're too big, then the chips don't get enough bandwidth, but their orientation and if they're long or more round, we typically just looked at small cases like this, but you could potentially if you had area 30 chips, there's a lot of different kind of shaped rectangles you could consider. All right, so we're going to do a. Let me first describe the MIP when you actually do want the exact solution. So the name of the game in designing these programs is to avoid redundancy, so the branch and bound or whatever the solver is doing doesn't spend a lot of time exploring essentially the same solution. So we're going to have a variable for each of the corners of each of the rectangles, and we'll order them, so you have an upper left and a lower right. And the way to do non-overlaps is to, you might think that that's inherently non-convex, but you can by introducing variables, you can turn it into a convex problem. So the way to model it is that if you have a chip or a subfootprint like this, and every other subfootprint has to lie completely in one of these 4 half spaces. Otherwise they'll overlap. You can. It sort of sounds like an OR constraint, but by summing up these slack variables, you can get around that and keep it convex. But the sort of the downfall of that, though, is that we couldn't figure out a way to calculate the area with just linear constraints and stuff. It's the product of the 2 sides, and so we ended up implementing decision variables as 0, 1 if a chip is in a particular subfootprint. Area is easy, just add up the indicator variables. Overlaps same way. And there's some subtleties about the objective function. There's a sort of penalty, so you don't cover 0 value chips. And then this term was for. Remember, I liked it if that small rectangle that only had 3 chips in it had high value chips in it, as opposed to putting it in a size 4 rectangle. Sort of a secondary consideration. All right, so this is the more geometric part. So we can't always solve, don't have enough time to solve all the MIPs. So let's do a greedy heuristic where we just put down the rectangle that covers the most valuable chips, and just keep doing that, constraining to be non-overlapped. And so you get sort of greedy solutions kind of look like this. And then if you run the optimal MIP on it, you get something like this. It's more compact. You tend not to have these little gaps and thin necks, because it does extra work to get an efficient packing. So our hypothesis was that if you had 2 different shifts that had similar looking greedy solutions, they would have similar looking optimal solutions. And so we went with that and decided to cluster these shifts by the similarity of their greedy solutions. And we did a k-means, kind of a k-means clustering on that, meaning you pick one cluster center, and then the next cluster center is the point that's furthest from all prior centers. And it's kind of think of it as a sort of a Voronoi property, but in this weird discrete space. And by similarity, I mean not just which chips are covered, but how they're covered. Are the rectangles nicely matched up, or you have in one layout you have a bunch of horizontal rectangles and the other one a bunch of vertical ones, and so you'd think that would be very dissimilar. So we define a kind of Wasserstein distance. I'm going to build it up from the bottom up. So the distance between 2 individual chips is just their L1 distance in this rectangular grid. The difference between 2 subfootprint rectangles is just going to be the sum of their chip distances. And I guess you could find if you were really doing Wasserstein, you'd find the minimal cost pairing of those sets of chips. But we just did a greedy pairing. It worked well enough. And then same thing for the layouts. set of rectangles for a particular shift. You just add up the distances between that. Okay. And, oh, shoot, that was what I was afraid of with putting on a different computer, this mess up here. But anyway, our hypothesis was borne out that within a cluster like this, the optimal and greedy solution values sort of tracked well. So it was good to just pick the best one from your cluster. But from one cluster to another, there's quite a variation in the gap between the optimal and the greedy. Here they happen to be the same. So it made sense to consider the different clusters and solve it on that. Here's some examples. Sometimes the I skipped the exemplar part, but you don't pick the center. You pick the best valued one. Sometimes the greedy solution is the same as the optimal solution, like here, but usually not. All right, let me. So we have open source software for all this. If you want to go play with it, it includes both problems. And I think sort of my main message was trying to be that there's a whole bunch of variations to this problem that they don't know how to solve and would probably benefit from a geometric look at it. And I can put you in touch with the guys who know what the real problems are. That's it.
Exactly 17 minutes. Any questions?
Yeah, done.
Does the non-overlap come from a hardware constraint? Because you can imagine if it's just going to cover, it will be letting them overlap with each other.
Yes, that's right. Yeah, just the way they implemented the hardware and the software that runs the system. Yeah, it's possible to do an influence the other way around. Like if you could show, you would do so much better if you could allow overlap. That it's possible for someone to go in and change the software. It's hard to change this satellite software, but not impossible.
Good. Yes.
Yeah, so how do we define the optimal compactness? Well, we didn't define the compactness. We used it sort of qualitatively. We defined the quality of the layout as just the sum of the values of the chips that were covered. And it just sort of turned out that if you solve the bit attacking optimally, you're going to be able to cover those little those sort of secondary chips that are surrounded by high-value ones. Whereas if you did the greedy solution, they would tend to get left behind, in little holes. But yeah, and we define the similarity between two layouts in terms of the cluster size distance, but it would be interesting to compare them based on their compactness as well. That would be something to look at.
Very good. All right. Let's thank our speaker again.